Okay, so the last type of line integral that we really need to look at here is if we want to evaluate a line integral where the path that we're talking about is a simply connected closed region. Okay, so if I want to get from point A to point B, except point A and point B are the same, and I'm just going in like a loop, that would be a simply connected closed region. So a simply connected closed region is one that, makes kind of like a pond. Now, it can't be a pond that has like two islands in it, like that one yellow diagram, or it can't be like a figure eight and cross itself. So a simply connected closed region would look like that. And we want it to be oriented for our purposes today counterclockwise, which means as you travel around the path, the inside is always on your left. Okay, so it seems like, Mrs. Vibber, I know what counterclockwise means, but when you start getting these funky shapes, counterclockwise doesn't always seem as normal as you think it would. Because if I have something like this, if I'm going counterclockwise, that goes this way, but this arrow would come that way, which for a half a second, if you're thinking about it, does feel almost clockwise. Okay. But anyways, a simply connected closed region, and we want one that's traversed counterclockwise. There is this thing that's called Green's theorem that says if you realize that you have a closed path, you can use this method to evaluate the integral. Okay. Now, before we get to that, we need to talk about integrals in this kind of new form, mdx plus n dy. That's called the differential form of a line integral. And really what it is it's f dot dr, but they've done half of the work for you. So off to the side here, I'm just going to explain mdx plus ndy is the same as mn, whoops, forgot my comma, mn dotted with dx dy, which is really just f dot dr. They've done the dotting part for you. So if you see a line integral in differential form, it's just really a work line integral halfway done for you. Okay. So Green's theorem says if you take your line integral and it's in the form mdx plus ndy, instead of parameterizing a path and dotting it and doing all of that, what you can do is say, if this is based on a closed path, which means also sometimes you'll see like a circle on the integral, it looks like this, and to indicate you have a closed path. If you are evaluating this integral on a closed path that's being traversed counterclockwise, instead of doing the line integral way of getting everything in terms of t, you can convert it into a double integral and then do to n to x minus to m to y, and then either do dy dx or dx dy to evaluate it. Okay, so let me just go through and do one example. I am not going to try to get you to understand Green's theorem perfectly because that's just not realistic given the state of what's going on right now. So if I want to use Green's theorem to evaluate this line integral, I would call this m and I would call that n. And Green's theorem would say that if I want to do the integral of m dx plus n dy, I can rewrite it as a double integral of n dx 2x plus 3y squared minus m dy. And the derivative of that with respect to y is 3y squared. Awesome. And then this dA means I can do dy dx or dx dy, whatever I want. Fine. I don't know what I want yet, because remember, when we evaluate double integrals, we care about the integrand, which is integrable with respect to both variables easily. And I need to compare it to my region of integration. The region. Okay. So C is the closed path from 0, 0 to 1, 1 along y equals x cubed. Okay. And then from 1, 1 to 0, 0 along y equals x. So my path would be that kind of crescent shape looking thing. and I am traversing it counterclockwise, so Green's theorem applies. So this right here is my region. And since my region looks like it's vertically simple, I'm going to go with dy dx. And my top y line is y equals x. And my bottom y curve is y equals x cubed. And then x is being traversed from 0 to 1. And that's the double integral that I can now evaluate in order to figure out the value of this line integral overall. So I'm going to evaluate this double integral. Come on, OneNote. Don't be silly. Oh, it's going to do that silly thing. Of course it is. Come on, close. So I'm going to evaluate this from x cubed to x and from 0 to 1. And then I have 2x dy dx. And so let's see. The antiderivative of 2x with respect to y is going to be 2xy from x cubed to x. And I'm going to substitute x and x cubed in for y, so that makes this 2x squared minus 2x to the fourth dx. And this is pretty easy to do by hand. So 2/3 x cubed minus 2/5 x to the fifth from 0 to 1 is 2/3 minus 2/5, which is some other number. And that's the answer. Okay. Had I not used Green's theorem and instead had evaluated this the old way, here's what that would look like. So I would be taking the integral of y cubed dx plus x squared plus 3xy squared dy along c. But c has two parts. So I would actually need to evaluate that along c1, evaluate it along c2. Already you're thinking, oh, I didn't think about that. Wow, it's a double line integral. Yeah, and I'm not even done yet. Now I need to parameterize C1, and C1 would be parameterized as t cubed comma t, and C2 would be parameterized by 1 minus t, 1 minus t. And then I'd have to substitute the t's in for the y's and the x's. And then I'd need to substitute the derivative of the path in for the dx's and the dy's. Then I'd have to multiply it. Then I'd have to, you see where I'm going here? I'm going to stop yammering at you and make you realize, oh my goodness, I haven't even done any calculus yet. And everything I'm discussing sounds like it's going to take a lot more time, which is why closed paths are an excellent place for us to have something like Green's theorem, where we say, you know what, even though I'm going from a single integral to a double integral, the double integral, trust me, is not going to be worse than doing multiple paths with multiple parameterizations, having to, what am I looking for? Having to substitute and distribute and integrate. This is much better. Okay, so Green's theorem says you want to take n dx minus dm dy and evaluate it using a double integral. So I'm going to just do one more. I said I was only going to do one. I'm going to do one more, but just do it faster, okay? So if I want to use Green's theorem to evaluate this integral in differential form, m is y squared, n is xy, and c is the boundary lying between y equals 0, y equals the square root of x, and x equals 9. So if this is my region, and I'm going to traverse it counterclockwise, okay, I can use Green's theorem because it's a closed region. So Green's theorem says take your original and turn it into a double integral, and then do n dx minus dm dy and evaluate that double integral. Wow, that's smaller. Thank you, math. So now I have y minus 2y. This is a vertically simple region, so I'm going to go with dy dx. The top part of my boundary is y equals the square root of x. The bottom part is 0, and x goes from 0 to 9. So then this is y minus 2y is really negative y. The antiderivative would be negative 1/2 y squared from 0 to root x. So that's going to be negative 1/2 x minus 0. And now I'm going to evaluate that with respect to x, which is going to be negative 1/4 x squared from 0 to 9, which is going to be negative 81/4. And there it is. Okay. This question follows up and says, how would this look if you used regular line integrals? You know what? It would look terrible. You know why it would look terrible? Because I have 3 separate paths that all connect to make a closed path. So I need 3 line integrals and 3 parameterizations. No thank you, but thank you to Green's theorem. All right, I am done. Hopefully you can at least follow along with the plan, even if you don't completely understand the applications. I hate doing it that way, but we are stuck in crisis mode, so that's what we're doing.